Hey there, and welcome. Have you ever been on a merry-go-round and picked that horse on a very outside, thinking it was the fastest? Well, it's not just in your head. It actually is faster, even though it's rotating at the same rate as the horse on the inside. Kind of weird, right? Today, we're going to unravel that little paradox. We're diving into two different kinds of speed, a concept that explains everything from a spinning record to planets orbiting the sun. All right, let's jump right into the big question. Picture it, a classic merry-go-round. You've got one horse tucked in close to the center and another one way out on the edge. The ride starts, and they both complete a full circle in, say, 30 seconds. So their time to do one lap is exactly the same. But the horse on the outside is definitely traveling faster. How is that even possible? And no, this isn't some trick question. It's what we're going to call the merry-go-round paradox. And trust me, once you get this, you're unlocking a key piece of understanding for all sorts of motion in a circle, from your basic trigonometry class all the way up to some pretty complex physics. So let's break it down. The secret to solving our little paradox? It all comes down to one really important idea. When something's spinning, the word speed can be a little misleading. It turns out there's not just one way to measure it. We're actually talking about two totally different things. So let's meet the two stars of our show today, angular speed and linear speed. Once you really get the difference between these two, that whole paradox we've been scratching our heads about, it just, poof, disappears. Okay, so here's the high-level view. On one hand, you've got angular speed. We use that cool Greek letter omega for it. All it cares about is rotation. How fast is that angle changing as it spins? Then on the other hand, you've got linear speed, which we call v. This is what you probably think of as speed. You know, the actual distance you cover over a certain amount of time. Let's dig a little deeper into angular speed. The formula is pretty simple. It's the angle you sweep out, theta, divided by the time it takes. Now, in math and physics, we don't usually use degrees. We use radians. Don't let that word scare you. A full trip around a circle is just 2 pi radians. Since both of our merry-go-round horses complete that same 2 pi radian circle in the same amount of time, guess what? Their angular speed is exactly the same. Okay, now for linear speed, this is all about the actual path you travel, that arc length s, divided by time. Imagine taking the circular path of the outside horse, snipping it, and laying it out flat like a piece of string. It would be way longer than the path for the inside horse, right? So since it has to cover a longer distance in the exact same amount of time, its linear speed has to be higher. It's just gotta hustle more. So we've got these two different types of speed. One is identical for both horses, the other is totally different. The big question now is, how do they relate to each other? Well, lucky for us, there's a simple, super elegant formula that connects them, a kind of bridge between the two. And here it is. Boom. V equals R times omega. Your linear speed is just the radius of the circle you're making multiplied by your angular speed. This one little formula explains everything. For our horses, the angular speed, the omega, is the same for both. But the outside horse has a much bigger radius, a bigger r, so its linear speed v has to be bigger. It's that simple. This quote right here just nails it. Every single point on that spinning merry-go-round, every horse, every light bulb, every little bolt, is rotating together so they all have the same angular speed, omega. But because they're all at different distances from the center, different radii, their linear speeds are all different. The farther you get from the center, the faster you're actually traveling through space. Paradox solved. All right, theory is one thing, but let's make this real. It's time to roll up our sleeves and run through a couple of examples to see these formulas in action. This is where it'll really start to click. Okay, first step, let's find an angular speed. Let's say we have a wheel that makes 3 complete revolutions in 2 seconds. Now, the absolute first, most important step is to get out of revolutions and into radians. 1 full revolution is 2 pi radians, so 3 revolutions is 3 times that, which is 6 pi radians. Easy enough? Now we just divide by the time. 6 pi radians in 2 seconds gives us our final answer, an angular speed of 3 pi radians per second. Now let's use our bridge formula to find linear speed. Imagine you're on a Ferris wheel with a 50-foot radius, and it's spinning at 0.5 radians per second. We know r and we know omega, so we just plug them into v equals r omega. That's 50 feet times 0.5 radians per second. Do the quick math, and you find out you're cruising along at a pretty zippy 25 feet per second. Check this out. This table makes our merry-go-round idea crystal clear. We've got a disk spinning at a constant 10 radians per second. Notice, point A and point B both have that exact same angular speed. Of course they do. They're on the same disk. But look at their linear speeds. Point B, which is 3 times farther from the center, is moving 3 times faster than point A. It's a perfect demonstration of V equals R omega. Okay, a quick word of warning. As you start tackling these problems, there are a few common traps people fall into. The biggest one, seriously, is forgetting to convert revolutions per minute into radians per second. Always remember, 1 revolution is 2 pi radians. Also, keep your units straight. Omega is about angles, V is about distance. And for goodness sake, read the question carefully to see which speed it's actually asking for. So you might be thinking, okay, cool, merry-go-rounds, but does this matter anywhere else? Oh, you have no idea. This isn't just for amusement parks. This distinction is fundamental to how so many things in our world work. Let's look at a few. Get this. That old spinning hard drive in a computer, if it's spinning at 7,200 RPM, the very outer edge of that metal disk is moving at around 100 kilometers an hour. That is literally highway speed happening inside a little box on your desk. Or think about riding a bike. When you shift to a bigger gear, you're changing the radius to get more linear speed for the same amount of pedaling. And really, this is just the beginning. Understanding this is your ticket to getting bigger ideas like torque, centripetal force, and even how planets stay in orbit. So, the big takeaway today is that anything that spins has these 2 speeds going on at once. And that simple little formula, V equals RW, is the bridge that connects them. It's why the outside horse is always the fastest. So I'll leave you with this. Now that you know the secret, what else is spinning in your world that's moving way, way faster than you ever realized? Thanks for tuning in.